speaker is Rimantas Lazauskas, and he will give a talk about the description of the neutron-rich helium isotopes, please.
Okay, so you are almost familiar with this for neutron missing mass distribution, which has been already presented by Miki-san and Hans this morning, obtained by fast removal of the alpha core from helium-8, and which created a lot of excitement, in particular due to presence of this very narrow peak at low energies and potential relation of it with tetraneutron resonance. So at the few years ago when this paper appeared, we have already studied the similar case, but in relation with other tetraneutron experiment performed by Shimura-san and Kisamori-san, but here it was a different procedure related with double charge exchange reaction with alpha core. And we observed that if the neutrons initially are in some compact state, so we obtain some broad distribution, unless you make some unphysical changes to your Hamiltonian and you produce some freaky structures like tetraneutron resonance. So if you look naively at this distribution and you look at the spectra or constitution of helium-8, so helium-8 contains 4 valence neutrons which are weakly bound to alpha core, by which holds only 3 MeV separation, 4 neutron separation energy compared to alpha particle, which is bound by some 30 MeV. And if you look at this structure, you naively can see that you have one structure somewhere at 30 MeV and other structure at around 3 MeV. So by the fingers, everything is very simple. So this give us idea with Emiko-san and Jaume Carbonell to study what happens if you consider broader distribution in initial state of the neutrons. At that time, we were not able to perform 5-body calculations, which are very complicated. So we decided to use very simple model to obtain initial distribution of 4 neutrons in before they emitted. So that consisted in freezing with alpha core and constructing some effective alpha neutron interaction, which reproduces dineutron and 4 neutron separation energies. And we straightforwardly obtained some sharp peak at low energies when studying this 4 neutron missing mass distribution, which, okay. So my goal of this presentation, so to go one step further and kind of remove this nail from the structure and consider 5-body model for helium-8. Okay, so if you study basically collisions in non-relativistic frame, I like to study it in configuration space, which is more visible. So if you consider that there is a scattering, so when one particle impinges on the complex structure like nucleus, there are multiple possible reaction channels. So elastic channels, basically rearrangement channels, and then all other possible recombinations of particles. How to take care of boundary conditions, because this system evolves into the infinity, and what you detect experimentally, it's a response far away from the reaction region. So there are conceptual difficulties to uncouple different particle channels related with all these different possibilities. And basically, Schrödinger equation is not sufficient to provide a mathematically sound solution for this problem. So the proper formalism was introduced by Fadeev in the 60s for free-body problem and extended by Yakubovsky in late 60s for any number of particles. So how does it look, this kind of formalism schematically? You need to uncouple different components into the function, which asymptotically will represent different reaction channels. So 1 plus n minus 1 particles, 2 with n minus 2, and so forth. So basically, your wave function should be possible to split in all these possible decompositions, but even further, to stay consistent, all the clusters should be decomposable in the same manner. So it's a kind of recursive procedure which kind of breaks your wave function in clusters and subclusters until you are left with single particles or particle pairs. So each with introduced component of wave functions will bring some additional constraint to your in top of your Schrödinger equation. So instead of solving one single Schrödinger equation, you will have to solve system of coupled differential equations. And because there are so many possibilities to split the system into the clusters and subclusters, number of these components grows very fast with a number of particles. Like in Lego game, you can, more Lego cubes you have, more possibilities you have to construct different creatures, yes, structures. So for 5-body systems, you have 5 different topologies of splitting your wave function. And actually, there are even more components which are based with possible permutation of different particles within these topologies. So if you look how number of these equations grow with problem size, you see that it grows dramatically. So they grow factorially, and actually this is a main limitation to solve the many broad-body problem using this formalism. And basically, I think that the physical limit is somewhere around A equal 5, which we have already reached. Because if you consider identical particle systems, you will have 5 coupled equations to solve. But if all the particles are different, it grows to 180. And if you want to pass one step further, you see already very dramatic increase in complexity. So merits of this formalism is handling of symmetries, which is very simple, implementing of boundary conditions for binary channels. This formalism is built for that, and easy reduction to system to subsystems. So when you solve your many-body problem, you already know all the possibilities if the system has some subcluster which is stronger bound, or which is when the bound state you are looking. Yeah. Okay, so let's move. So my idea is to study helium-8 and construct a model for helium-8. So physically, I'm limited to 5-body system. So idea is to imagine that the alpha core is structureless particle, and then you have 4 additional neutrons So there are many studies of the helium-6 and helium-8 system, mostly using simplistic interactions of alpha neutron, but also some ab initio studies. And you see that ab initio studies, and one of most advanced of them, like no-core shell model, they struggle to describe the system. The convergence is very slow, and if you check the last point at which we obtain the solutions, you can see that at this point, helium-6 is not bound relative to alpha particle, and helium-8 is neither bound relative to alpha particle or helium-6. So if I try to use this kind of wave function in my calculations to propagate for neutrons, I don't believe they can be very useful because they don't have any asymptotic relative to this distribution of for neutrons. Okay, so that is the problem of this slow convergence. It's basically the same problem as for the delivery guy or delivery company. So everything is fine if you have to deliver the spherical object, you straightforwardly put into the square box. But if your object is kind of strongly deformed, like a ski, you can try to fix into the square box, and you will and either your cost will blow out because you have to use extremely large boxes, or you will cut your box and fail the delivery. So basically, it's the same problem here because you try to describe the system in the spherical box by confining your particles, and it simply doesn't work. So what are ingredients? So basically, to construct the alpha nucleon interaction, we need some data, and data is abundant. Also, you can have the experimental data, or already this neutron alpha scattering is quite well established in numerical calculations. You have different groups with different formalism, as well myself, also no-core shell model or green function Monte Carlo, which obtain the reasonable description of the phase shifts using realistic nucleon and free nucleon interactions. So there are also quite a few modelizations of the effective interaction. So for probably one of the oldest is this potential by Bang and Ginu, which contains two, how they called it, so which contains six parameters, but you see if you want to construct this interaction in a kind of operator form, you straightforwardly produce the deeply bound S-wave state, because in this system you have resonant P waves and due to Pauli blocking repulsive S-wave. So therefore, if you wanna go beyond the neutron alpha system, you have to handle somehow this spurious S-wave state. So standard formalism is to project it using Gaussian formalism, project it somewhere to infinity, and this kind of doesn't affect any phase shift, so very, very practical tool. There is other possibilities how to handle with this spurious state. So instead of projecting out the deep state, you can project out some kind of harmonic oscillator state, which this model called OCM. But actually, this harmonic oscillator state is in single particle coordinates, which you have in the formulation of the Pauli forbidden state. So if you try to make a formulation how to transform this wave function into relative coordinates, you see that rigorously you have project out one kind of one deep state harmonic oscillator in relative coordinate and some fractional parts of other states. And this brings some more complicated formulas like fishbone potential. So these potentials with a few parameters like 6, we are able to describe very well with low energy data of neutron scattering on alpha particle. But if you try to calculate helium-6 straightforwardly with these interactions, you see that you are strongly under binding the system. Instead of getting some 1 MeV of bounding energy, you get not more than 200 keV. There is exception of this KKNN potential, but it's basically due to less accurate description of nucleon alpha data. Okay, so natural solution would be introduce a free body force to resolve this problem. But who likes the free body forces? So who? You. Okay, Bira, is not surprising because you had never implement them. Okay, yeah, so I try to do anything to avoid these free body forces. So the first idea which came to my mind is to use softening using SRG. You know that from previous calculation, if you apply SRG, for nucleon-nucleon interaction, you have underbinding of triton. So, but if you soften this interaction using SRG, you don't affect nucleon-nucleon scattering data, but you can manage generate some additional attraction. But when I apply to these potentials for alpha neutron case, helium-6 doesn't move, so its cardiogram is completely flat. So, so as I said, natural remedy will be free body force, but there is a kick in this game. But already, if you look at this interaction, you see that even having underbinding of helium-6, you have already mean square radii which are compatible to experimental data. So if I, with additional force, squeeze it even more, so directly this radii will fall down, and I have too much compact object, and I am looking to describe this broad distribution of the neutron. So actually it means that your free body force should have structure, so you should have some repulsive short range behavior which doesn't let this system to collapse, and have attractive part to increase the binding energy. And the same calls from simple scaling arguments. If you put very attractive free body force, in the end it will overshoot two-body interactions and will collapse the system if you put many neutrons in it. So it will be dominated just by attracting free body force. So I started to study how to reproduce with phase shifts, and I observed that they like very much some deep potentials, like taking simple Yukawa potential, you can easily with even with here with a single parameter for each partial waves, basically it was 5 parameters which I used. You have much better description than in previous models. But this generates deep states. So it's something like Bira likes very much. So deep states in P waves and in S waves. So okay, I thought, and it still does not resolve this problem of the underbinding. The helium-6 remains bound by 100 keV instead of 1 MeV. So I said, why should I use this OCM, which kind of drives your forbidden state far away? I know that I control my physics just up to 20 MeV, up to breakup threshold of the alpha particle. So why just all this rubbish I just throw out of my garden? So instead of projecting it to infinity, I just project it above of 20 MeV, and like this I will get some additional binding for helium-6. And it works, so if you project this state at some 20 MeV, around 20 MeV, you can get a good description of helium-6. But unfortunately, I was very happy, but and this model kind of reproduced very well other systems in helium, other isotopes, so helium-6 2 plus resonance state in helium-7, so 3 neutrons plus alpha core, and also helium-8 binding energy is not catastrophic. But I have not so straightforwardly. It has catastrophic consequences of root mean square radius of neutrons in helium-6. So you get some very, very small root mean square radius compared to what is expected. So unfortunately, I had to go back and work with the standard with these other models and compensate the lacking binding energy in helium-6 by adjusting free body force. So in the end, I have 3 models. This is my personal one with this rubbish out of your garden. And these other ones with fishbone and OCM, where I introduced free nucleon force, and this is without free nucleon force. So I went back to calculating this for neutron energy distribution using this wave function, and I get that for this cliff potential, which gives a very small radii, I get very broad distribution of for neutrons. While if I use free nucleon force, I managed to have more reasonable radii for root mean square radii for neutrons, and I have a narrower distribution which are comparable with ones which we get in our simplistic calculations. Still a bit broader, but these results are very recent, and I cannot exclude that they have there are still plenty of errors in my code, so it's very preliminary. So that's it. I move to conclusion. So helium isotopes are ideal test ground for cluster methods and phenomena related with Pauli exclusion principle. So there is this striking dynamical phenomena observed by Due et al. Experiment with a sharp low energy peak appearing in for neutron distribution, and this, in explaining this feature, I think that the key is in understanding and describing structure of helium-8 nucleus. So that's it.
Thank you very much. Okay, now paper is discussion. Any question or comment?
So thanks for this nice talk. Could you go back to the last figure that you showed? So this blue dashed curve, PUP 25 MeV, what is different in this?
Okay, so I forgot. Okay, so these curves I constructed with assumption that you are removing a core without transferring momenta to 4 neutrons. And this one, I suppose that there is 25 MeV transmitted to 4 neutrons. So basically, it doesn't change the relative energy distribution in the initial state, but we have this 25 MeV of center of mass motion. And when you kind of do is kind of the core transmits some momenta to the 4 neutrons, so it means that the neutrons, in some sense, they are emitted from the region closer to the core. And that's why you get this broader distribution, because they are less correlated and more energetical.
Any other question? Okay. Tobias or Daniel.
And so this one would match better probably with broad peak in the distribution.
So I want to see if I understand something, right? So this is your very interesting result for, what is this, like you would call this non-point-like production of the tetraneutron? This is just how the kinematics at which you have calculated this correspond to what?
With 25 MeV?
No, just the green, red.
Okay, so green, red, and so on. So they are supposed that for neutrons, that the core is removed without transmitting any momenta to 4 neutrons.
Okay, so the initial momentum distribution for the 4 neutron state is whatever it was in the bound state?
Yeah, so if you consider that this helium-8 is a target, yes, it's not moving.
Yep.
So you remove the core, and if you measure 4 neutrons and try to to calculate their relative their center of mass momenta, it will be 0.
Okay, very good. So then if I go back to your first slide, you had this result that I had missed when you published it in 2017 for point-like production of the tetraneutron?
No, it's this one.
The one by double charge exchange?
Yeah, it's not actually the point, but the initial distribution of the neutrons, because it was double charge exchange with the alpha particle. So he claimed that cinematics is like that he makes a double charge exchange and alpha particle doesn't move. So it means that kind of initial distribution of neutrons should correspond the density distribution of alpha particle. If you disregard all the effects related with some operator of this transmission. Yeah?
Okay, so this is a
contact.
So then, yeah, because the alpha particle is then obviously much more compact than helium-8.
Yes.
And so, to state the obvious, this looks a lot more like what Hans was showing this morning.
Probably.
It looks more like, I don't know whether
it looks more like this broad peak, yeah?
Ah, okay, I see. Okay. So you're saying that if I look at the energy scale, this energy scale is much larger than the energy scale Hans was showing this morning?
Hans was showing just the beginning of it.
Just the beginning, yeah, okay. So then,
So, but-
what's the, like, so I always like to ask, like, small compared to what, big compared to what, right? So if this is like production at some short distances and helium-8 is large distances, what defines the boundary? Or is it fuzzy? Is this peak just going to move down as
I would say that there is no boundary. It's just what you pay, what you get. If you remove neutrons from the fatty MEV distribution, you have something centered about the fatty MEV distribution. If you remove them with where they have free MEV, they will kind of prefer to stay at free MEV.
But you're saying more than that, I think, right? Because you're saying if you
Yeah,
remove
but
them,
that's
it broadens too, right? So
How?
So if you remove them from 30 MeV distribution, not only are they centered at 30 MeV, but they're also much broader, right? But if you remove them at at 0 MeV, then they're centered very close to 0, and the distribution is somehow much narrower. Did I get this correctly?
Okay, so it's the response is with overlap, yes? Yes. Yeah. So if in your initial state you have kind of a distribution which has low momenta, so you will get low momenta. Yeah, if you get with high momenta, you will get some introduction of a high momenta, which if you have already only high momenta, you will get only high momenta. So. And then, of course, everything is mixed together and complex. And
Okay, any other question?
So in essence, what the experiment measured is the wave function of helium-8?
It will be too simplistic. No, it is. Yeah, everything is messed up, so it's a complicated thing. But there is a good component of this in all this business. So you have also this one, but there is it's an overlap. So you have a big contribution of this in.
Any other question? Okay, Tobias. Okay.
Is going a little bit further in this point, Rimas. I remember the extreme dependence on the height of the peak with the scattering length, with the neutron-neutron scattering length. And I was wondering now if from where, if this dependency is mainly from the final state interaction between the neutrons, or also the initial distribution is relevant?
There are two things. If you also don't have this di-neutron correlations, if suppose that neutron-neutron scattering length is small, so you will also have a very broad distribution. So probably because this overlap will have extended part of this thing.
Let me try and ask Tobias's question in a slightly different way. If I took the neutron-neutron scattering length to infinity, would the structure of helium-8 change very much?
Helium-8, no.
There we go.
Okay.
But this thing will change.
This is what we also see in
Yeah.
two neutron halos, right? Exactly. I mean, this is a much more sophisticated calculation, but sorry, yeah. This is in two neutron halos. This is exactly what Goebel calculated, right? But this is much more complicated and sophisticated calculation, but it's exactly the same principle that the structure is unaffected by ANN, but the final state interactions are highly sensitive to ANN. Yeah.
Perfect. This is the separation I wanted. Perfect.
Okay, any other question? Still, we have some 5 minutes because Rimas, so the talk is so sharply 25 minutes, so then we have a lot of time to discuss. Okay, Miki-san.
Miki.
Thank you very much for the nice talk. And I have one question, maybe a little bit away from this, but can you calculate the 2-proton removal from helium-6, producing the tetraneutron?
2-proton removal from helium-6.
Yeah, you have to break the alpha particles. That's,
Yeah.
I understand it's very difficult for
Yeah,
you,
it's,
but
you should make some assumptions how you break this alpha particle.
alpha particles.
Because in this scenario, we still kind of consider that alpha particle is structureless.
I see, I see. But actually we discussed yesterday about the effect of the three-body force, and in this particular case, we never see it, right? The effect, this triangle, 2 triangles, one is only with the two-body interaction.
Yes.
The other is with 3 nuclear force, but there is very thin difference, right?
Yeah.
But yeah, this is actually natural because these 4 neutrons are really well separated in helium-8. But if we start from helium-6, at least 2 of the neutrons are in the alpha core, so they are in close distance. So I wonder if, in that case, 3-body force effect might be non-negligible, I would say.
Somebody should look at this green function Monte Carlo calculations, but I guess that we won't be so much affected by
Yeah, before looking at it, I think we cannot conclude it. But yeah, if you can calculate the 2-proton removal, that will be very important for us. But okay, this is a comment. Thank you very much.
Okay, any other question? Okay, I have a small question. And in the case of helium-8, so in the 4 Newton state, you include the 3-body force or not?
in these last calculations,
Yes.
I have not included, but
Okay, just only the 2-body and then interaction.
yes, but in these ones, we have also performed.
No, in the case of helium-8.
Helium-8 now,
Okay, just only. But in the,
because it doesn't affect,
yeah, I think, just a question, you didn't include.
no.
Okay, and in the case of helium-8 calculation on the last slide, then you show up KNN plus 3-body force. What is 3-body force? Is a phenomenological
It's a
force?
free-body force between alpha,
And
neutron,
N.
neutron, yes.
Okay, to reproduce the binding energy of helium-6.
Yes.
Okay, it's some Gaussian simple potential.
It's, yes, I added I had to add 2 terms, one repulsive and one attractive.
Okay, like us. Okay, I understand. Yeah, just so any question. Okay, so okay, almost the time. Then okay, let's thank Rimas again. Very good.